Okay, so yes, yeah, thank you all for being here. I am giving a technical introduction to our adaptive code. So the idea is so it's not going to be the usual scientific talk you would hear at a conference, but it will rather dive in a bit more in the programming concepts and what I think you should know when working with this code. So if you have any question or something is unclear, please interrupt me right away. The idea is, there's still somebody coming. The idea is really to record this talk and then give it, put it online somewhere so that it's sort of a documentation of the source code. And the more interactive you are, the better it is for this video, in the hope of not having to record it again. Okay, so well, as I said, it's a technical introduction, but I still wanted to show just some videos first because it's otherwise going to be a very dry talk. This is what I myself use this code for. This is an insect model with flapping wings, and we compute the flow around it. This is based on micro-CT scans. We're not going into detail. And this is just to show you that it's beautiful and that it works, and why this code is interesting for other people as well is shown on this slide, because we see the same simulation, but we see also the numerical grid. And I don't know how good the transmission is on your screen, but you should see that a region of densely packed grid points and blocks is following the beating wings here. So in other words, this code uses a technique called wavelet-based multi-resolution, which automatically adapts the grid to the solution which the flow has right now, so that the resolution is put where it's needed. This is in contrast to earlier codes where we used the Fourier approximation and the grid was fixed in time, and you must be sure in those cases before running a simulation that your grid is sufficient, or verify it afterwards with the convergence tests. But these codes, they adapt the grid to the solution. And this is a little bit more visible on the next slide, where this is a 2D problem. It is just 3 vortices that are merging, and they are in nonlinear interaction, which means they produce, we start from a relatively simple solution, just 3 Gaussian blobs, and they form quite a complex structure by nonlinear interaction. And as you can see, the code actually refines the grid where all these fine-scaled features are. And as I said, it's a technical introduction, so I'm not going to put a lot of weight on how this is done mathematically. We use wavelets for this grid adaptation. There is other choices available on the market. You can also just look at the vorticity and think, okay, where do I have a lot of vorticity? And we believe that this wavelet-based approach has some very nice properties and advantages, but I'm not going to go in the details of that. It's going to be the topic of a different presentation. So the content for today, what I would like to tell you about is, first and foremost, is WABBIT's data structure. So how is this time evolving grids handled in the code? I will spend just a quick look at the solution algorithm and how this time stepping works, and what equations are solved, and how this is the interface WABBIT with what we call the physics modules. So I'm using the terminology that we use in the code here, which is sometimes a little bit, well, let's say clumsy, but I just keep the same words that we use in the code. And so just right from the start, we actually distinguish between WABBIT and the physics modules, and WABBIT is the part of the code that manages the grid. So it is responsible for all what's happening on MPI, load balancing, ghost node synchronization. We will go more into details later. And it ensures that the grid is adapted to the local solution. And now what happens on the grid is called the physics modules, and they implement different equations, the statistics that you use for these equations, and so on. So you have this sort of equivalency, WABBIT handles the grid, and the physics modules, they handle what's happening on the blocks. But we're going to see that a little bit later. Now, first, this is really the super top level introduction to the code, what you do, how the code is used. So you will first have to obtain the code. I recommend using Git for that. You can also download it from the website. In a nutshell, you will have to build the code, so translate the source code in binary. To do that, you will have to use the HDF5 library, compiled with the same compiler, and you give it the location of that library in the environment variable HDF root. Not going into details. And then to run the code, you have the usual MPI command. In this case, it's on 1024 CPUs. You have the code, and then you feed it this INI file, and this INI file really configures what you want to do with the code. And then the last argument, you give it the available memory that you want the code to use. And that depends on what you are currently doing. If you're doing development on your local machine, on the laptop you're sitting in front of, then you will probably give it slightly less than you have in the machine. So I have a 32 gigabyte RAM in my machine, but I usually run it just on 8 because I'm using this computer for other things in the meantime. But if you are running it on a supercomputer, you will usually simply give it the amount of memory that you have on the machine, because there's very little background processes running. This supercomputer does only one thing at a time, which is run this code. So all the parameters.
I want to be clear. So should I use what I need, or should I use on available memory I can?
So on a supercomputer, you will use what you have. On your laptop, you will use what you can afford. And if the memory is not enough, because that can, oh, I'm sorry, I will just turn off this ringing because how can I do that? I have to stop screen sharing. So on a, what was I saying? So it's very difficult to predict how much memory you will need. That depends on your case. If it's a case that starts like the 3 vortices problem from a very coarse problem and then evolves super fine scales, then probably you need much more memory at the end than you need at the beginning. And the code will just abort with a message that it runs out of memory if it does so. But on a cluster, use simply what you have. So, and then maybe you will allocate much more than you need, but on the cluster, that's not a problem. And we will come back to the memory allocation a little bit later. So as I said, you have this INI file, which you use to configure all user-defined parameters in the code. That's like, let's say the viscosity, for example. If you change the viscosity, you simply change this file and then you run the code. So there is no need to recompile it, right? If you do a change that is just a parameter, then you will simply run the code again and change the INI file. However, if you are doing something that has never been done before with this code, so you implement a new, I don't know, geometry, you want to study the flow around the cube, let's say, and you implemented a cube, then you will have to recompile this code. Yeah, and this is just, well, the memory, usually you use the memory that you have available. And we will see later how this is actually handled in the code. Right, so, and there is a few things I wanted just to draw your attention to without, again, so it's mostly I'm dropping keywords and explaining some concepts, because I think it's important that you just have heard that these concepts exist. And then if you have questions, we can clarify that later. But you cannot ask the question if you don't know that these things exist. So I wanted to start with the pre and post processing. So you have this collection of Python tools, which is also on GitHub, and you can just download it the same way you download the adaptive code itself, and it contains a lot of useful scripts that we use to pre and post process code. So for the pre-processing, it is probably the most important is this called WABBIT check INI file .py, which runs just a simple test and collects some often made mistakes, like you said, a negative block size or something like that. So these things will be checked in this Python script. Of course, it's not exhaustive. So every time you do something stupid, you should ideally add a check to this Python routine that nobody ever will do this mistake again. And it's usually done. So on my supercomputers, I have put this in the job submission wrapper so that it checks it every time. Another thing which is very important is this WABBIT resume backup. It's also very simple. You can, well, it's just because the code usually is used for long simulations, which take a couple of days. But on a supercomputer, you usually have about 20 or 24 hours to run a code. And so the code is interrupted in the middle and it has to be restarted from backup, so from the files that it writes. And for post-processing, just the two that I want to discuss is the WABBIT time left. It gives some statistics about the performance, the current performance, and this script HDF to XMF, which is a wrapper for ParaView, so for visualizing the flow data. And we start just simply with WABBIT time left. Can you read that still on your screens? It's a bit tiny, maybe. Okay, okay. There's no mic, but
I think it's okay.
Okay, maybe I hope in the recording it's going to be okay. So basically, you just call it with WABBIT time left, and it gives you some statistics on how many cores it is running, how many CPU hours it consumed already, and so on. And in the end, it gives you a prediction of how long the simulation will still run and how much CPU time is going to be consumed by the end. It's a prediction, of course, right? So if something explodes at the end, then of course the CPU time will differ from this prediction. And what you see here is the cost, the current cost in CPU seconds per grid point and per right-hand side evaluation. And why am I telling you this is simply that this numbers here over all the time steps and over the last 20 time steps give you when you are developing something, give you an idea of how good a job you did. So if you have a little bit more experience, you check this number on many of your previous simulations, and then you program something, and all of a sudden it goes from 10 to the -6 to 10 to the -4, then you know you did something not so good. So simply to have that in mind, and again, maybe no need to understand all the details of this processing scripts. What is interesting, what is important also is this wrapper HDF to XMF, because HDF5 is, well, I think it's more or less a standard now in scientific computing. This is where we store our data in, but HDF is a very, very general format. So it can be used for everything, not only for flow data, but also for text or whatever, images and so on. And because it is so general, you need to describe your data somehow so that the visualization tools know what they find and how to interpret the data that they find. And this is simply the HDF to XMF PI. Again, I'm not going in the details of all of that. It creates just a small, well, sometimes small, sometimes large file, which is called, which is an XMF file. And this is the file you read in ParaView. And just a last remark on that. Oh, I'm sorry, it's getting even smaller now. If you pass -H, maybe you can see it, maybe not, to these Python scripts, then you usually get a help. So a description of the parameters that it gets. Again, we don't have to look at it right now, but it is just useful to know that you can do that. Okay. So as I said, the idea is more to drop some keywords and to show you that things are there rather than explaining them in detail. This was the pre and post processing. And now we want to go to the actual topic of the talk, the WABBIT code, and primarily how it handles the data. So on the left here, on the right here, you have an example grid. This is a very simple grid just for illustration. It has So what you see is the code uses block-based refinement. So that's the first thing to notice. So we always have one of these little squares is a block, and this block features several points. And that's one of the key differences to older codes for wavelet-based grid refinement, where this was points and not blocks. There's reasons to do that in blocks. It is much more efficient, I think. And well, this was the main motivation. And so you also get a feeling how this actually works. We start from a certain level. So at the beginning, the entire grid is just one block. And then we refine that. We refine this once, then we end up with 4 blocks. So the blocks 1, 2, 3, and a block which has already disappeared because we refined it again. So basically what we do in the code is we simply refine blocks by substituting one block by 4 blocks, or the other way around, we merge 4 blocks into one mother block. And in the INI file, this is just from the INI file, we set this block size, so the number of points that you have per block. And the usual setting would be the one here in gold. Just for 2D and 3D, you just give it one number, and then it's in all directions, it's the same number of points, but you can specify a number of points on the block in each direction separately if you have rectangular domains, for example. Although I would not recommend doing that because, well, it's probably not the best idea. Well, one thing, well, this number, how you determine this number is again a different story. So you can look at the paper that we're about to publish. I put it on archive. You can check it out. It's mainly for performance reasons. And you have to keep in mind, the higher this number is, so the more points you have on each of the blocks, the more regular your data is, right? If you go in the extreme case where you have a very large number, you just have one block. And this is for a computer very nice because it can just run an extremely fast loop. But it is also very dense, right? Because you do not have an adaptivity anymore. So you have more points. And so the balance that we thrive for here is a smaller number of block nodes. Block size means that the grid contains less points overall, but at a higher cost per point, because we have more blocks to handle. We have more MPI communication and so on. And a larger number reduces this cost, but it also increases the number of points. So as you can already feel, there is sort of an optimum in the middle. It is a very shallow optimum, so it's really not super important which number you put in. I recommend between 17 and 32 and 33. It has to be an odd number. I didn't put it on the slide. Oh, yeah, I put it. And other than that, you can put what you like. And another remark that's very important is the condition called gradedness. So what we have on the right is a graded grid. So this is a grid that has at most a difference of a factor of 2 in resolution. So we will, for example, what we cannot do now is divide block number 3 again into 4 smaller blocks, finer, like higher resolved blocks, because then here we would have a non-graded grid, so a factor of 4 in resolution. Now, what would happen if for some reason we decide to refine block number 3, again creating 4 finer blocks? This would mean in the code that blocks 2, 3, and 1 also would refine. Okay, so this is sort of well, a non-local effect. So I decide to refine block number 3, and I get a lot of other blocks that I need for this gradedness condition. So maybe you ask why the gradedness is actually used. It is mainly for numerical reasons. So the discretization of these grid jumps is tricky, and it gets trickier the larger the jump in resolution is. And also it is very tricky for the MPI synchronization. So let's say it is already a nightmare to code this for a grid jump of 2, and for arbitrary jumps, it is even, well, I would not want to do that. Now, our grid has no holes. By that, I mean the condition of completeness. It simply means that if we coarsen the grid, we cannot coarsen block number 3 just on its own. It has to be merged with the blocks 0, 1, 0, 0, 0, 0, 1, 0, 2, and 0, 3. So they are all merged together so that there is no hole in the grid. Which also means you can coarsen this grid region only if all the 4 blocks satisfy the coarsening condition. That's another thing. Oh yeah, just one remark, because it happens in the code quite often. In the literature, many people use the names father block and brother block and so on. And at the beginning, we wanted to gender this code. And so in the nomenclature in the code, if you merge these 4 in one block, it's called the mother block. And the 4 blocks are called sisters or daughters, just so that you're not confused. Right, so and now if we go to the block level, and this is a central point. So what is a block? A block is characterized by its size BS. So in this case here, this is 5 grid points. It has a number of ghost nodes, G, which is in this case 2 ghost nodes. So this layer of open circles is the ghost nodes, and it is characterized by a tree code. And this I will show a little bit later what it is. And from this tree code, we can derive its level. So sort of the zeros level is just where we start. The first level is refined once, second level is refined twice, and so on. And from this level, we can then compute the spacing. So the distance in physical, the physical distance between 2 points, because in the memory they are simply always 2 points, but in physical space this means they are coming closer together. And of course these blocks have an origin. So this lower left point here is called the origin x0, and this is of course important if you distribute the blocks in space. Now, if we just take a 1D example here, this is, we have it on the same slide, on the next slide. So maybe I just skip it. So this is the just a 1D cut of this block. Here you have what we call the interior nodes. So these points are actually belonging to that block, whereas these ghost nodes, they are in fact synchronized with neighboring blocks. Okay, so this is the thing. So if, for example, we want to compute some operator here with the second order finite differences, then this is how this looks like in the code. We loop Fortran ordering, column major ordering. So we start with the while loop, and we loop over the interior points, so from g+1 to bs plus g. As I said, this is a vector, so in the code, it looks like that. We loop over x, and then we compute some derivatives from some arbitrary field, which I call u here. We compute the derivative in x. So this means we take the next grid point in x direction, previous grid point in x direction, and we multiply it by this inverse of the spacing and times 1/2. So this is simply the second order central finite difference as it's taught in universities, in textbooks. This is the same in y direction. So here simply what changes is that the index y is 1 up and 1 down. And then we store this result. Here I called it diff. It's not really a diff, but just to give an example how this would look like if I were to compute the operator udx plus udy and store this in an array called div. We will check out these indices towards the end a little bit later in the presentation. So this is how a loop over a block looks like to compute a derivative, for example. And you should really not modify the ghost nodes ever. So it's simply a rule of thumb. If you change something in these open circles, that's probably not a good idea. Let's say like that. So the data structure, as promised, and this is just the very, very basic concept. We have 2 types of variables in the code, we separate into light and heavy data. The nomenclature is from the literature. It's maybe not the perfect nomenclature, but it is understandable. So light data means we associate a low computational cost with it. This is, for example, the information about the grid topology. So you have a long list of blocks and you want to know where they are in space. And this is called the light data, or metadata if you want. And these data are redundantly available on all CPUs. So this is kind of a crucial concept. We do not parallelize this light data structure. All CPUs have at all times the complete grid topology. They don't have the complete data which lives on this topology, but everybody knows how the grid looks like at all times. And what we did in a few years back, and this is turns out to be a very good idea, so all variables in the code which concern this light data have a prefix called LGT, and the most important one is called LGT block, but I will explain it a little bit later. But this is the state vector, and unfortunately, sometimes our nomenclature is not so consistent, because this would probably be good to call it LGT state vector or something like that. Now, in contrast to the light data, you have the heavy data. And this is where we actually spend our CPU time on, computing derivatives or whatnot, what have you, time stepping. And this is the actual flow data. So the data on the blocks, velocity, pressure, divergence, all these kinds of data types. And those are, of course, parallelized. So any of the CPUs only holds a subset of the entire data. And it has no means to access the data from other CPUs, as it's normal in parallel computing. And the variable code is heavy, HVI, and most importantly, heavy block. So this is, again, the state vector, which holds the actual flow data at any one time, t. Okay, and unfortunately, we have quite a few of these variables, which is actually the motivation for this presentation. So what you see here is a small part of main.f90. So this is the main program. And what we do in WABBIT, we pass these main variables, let's say. So what is important for the grid, the data on the grid, we pass them as arguments. And this is kind of the standard way. I'm just telling you that we do not have these global variables that you see in some research codes. And as you can tell, we have quite a list of them. So the first one is this heavy block. You can tell by the prefix heavy that it's parallelized. So this is a heavy data structure. This is the state vector. And you have a total of 5 indices. The first ones are simply the spatial coordinates, x, y, z. Then you have the components, so the vector components of the state vector, which, for example, in the case of the artificial compressibility, this would be ux, uy, uz, and p. So a 4-component state vector. In the compressible Navier-Stokes equation, you would have 5, for example, the density rho, the 3 velocity components, and then, for example, the pressure or the entropy, or what you can use for that. And the last index here is the block index. And this all is, so really our whole heavy data is in one very large array. And from this, you can see why we did these design paradigms that we use. All blocks have the same size. And this is a necessity. It's not because we like to do it, but if the number of points in x, y, z changes for some blocks, then of course they do not fit in such an array anymore. So this is a central point that I'm trying to make. We tried really our best to keep the code simple by making design choices that limit the flexibility of the code, but have the benefit of simplifying the code significantly. So our grid is one array, even though it is an adaptive grid. And that's the message that I'm trying to pass. It's not a structure or something that you would use in C. Now, you have a few more of these arrays. You have heavy mask, which is unfortunate that you have it, but it's like that. I will explain a little bit later why you have it. This is used for the volume penalization. It is the mask function used to encode the geometry. In the videos that I showed in the very beginning, it's the fly. You have heavy work, and this again is an unfortunate name, but we don't, well, sometimes first choices are not always so very good. And this is actually a work array that contains the memory needed for time stepping. So this has the same dimension as heavy block, but it has one more, which is the right-hand side register. For example, if you use a Roman Cotta 4 substep time marching scheme, this last index would run from 1 to 5, where you have the old data, you have the 4 substeps of the RK4 scheme in there. This is the memory you need for time stepping. Then heavy temp is the actual work array. So this is used, for example, to compute the vorticity, if it's stored or something like that. In the case of compressible Navier-Stokes, and I think, well, if there's questions, we can ask it later. This is used also for state vector conversion, because the compressible Navier-Stokes module solves the equations in skew symmetric form. So you have some square roots of rho and so on in this, and sometimes you want to store the actual variables, so the velocity, the pressure, and the density, and not these derived ones, and heavy temp is used for this conversion. And this last one over here is an interesting one, which we'll come back to later. It's called heavy neighbor. So this tells us for any one block, who are my neighbors? And this is important for the MPI parallelism. It is not important for solving the differential equation. And you can see also this is of type integer, so it's a different type of array, even though it is parallelized as well, so it's heavy in that sense. And over here we have the LGT block array light. So this is actually the grid, how it looks like. The list of blocks is associated to a position in space and a resolution, a level. And all of that is stored in this LGT block that we're going to explore a little bit further. This one here, LGT sorted numeric list, is very similar to the LGT block array, but different. It's used for block searching. I will explain it later why we need both, and ideally at some point in the future we will get rid of one. And these guys over here are called the active lists. You don't need to understand it right now. I have many slides on that because that's sort of a key concept. You just need to know that they exist for now. So these guys are the variables that are important for the code, like say main variables, I call them here. But of course you have hundreds of additional parameters. So I don't know, what time stepper you use is a character, or what is the block size, and so on. A lot of these parameters, and they are all passed in one go in this derived data structure. In C, this would be a structure. In Fortran, it's called derived data type. The definition is over here, and it is read from the INI file into this param structure in this function. For example, you have the block size, the number of goes, the dimensionality of the problem. So let's say if it's a 2D or 3D problem, all of that. And this is maybe for Hang important. So we did a better job in this code than we did in the Flusy code, for example. We do not have these global variables everywhere in the code. So most of what we use is either passed as an argument or in this params data type, and only like the precision, this kind parameter RK and IK and T size, for example, they are really global in the code in the module called module globals. Oh yeah, by the way, which is nice, everything that generates a module also has this in the file name. Okay, so these are the main variables, the main parameters. Again, if you just look at the source code, you will see how many they are and what they all do. And now, as I said, so we have, this is a typical WABBIT grid, right? It's the same grid as we have seen before, just the refinement is on the other side, and I've plotted just some data. This is what I would call the grid layout. So it just plots all the blocks and takes this origin and the spacing into account. So this is what you would like to see, you yourself. But what the computer sees looks like that. So I just colored here 2 blocks, and so basically, regardless of the resolution, they have the same size, right? So they all go in one array. They are not necessarily ordered in any way. It can also happen that sometimes you have a hole in this array. So what I visualize here is the heavy block array, the state vector. And this pink one over here would be x, y. This is a 2D problem, so z would just be 1. First component, and let's say block number 17. So this subset here is an actual block data, saved, as I said, in one contiguous array split among CPUs. So you see this kind of, what do you call it in English? This Abbildung, I don't get the word. Well, anyhow,
Mapping?
So this is, say it again, please.
Mapping?
Mapping, yes, thank you so much. It's too early for me. So the mapping from grid layout to memory layout is done using this LGT block array, and this is how it looks in memory. And you also see what I point out here. What we do in this code, we allocate in the beginning and only once this gigantic heavy block array, regardless of how many blocks we use. And this is important because allocation takes a finite amount of time. It is not for free. So we just allocate what we have and then use only a subset of that. So in this case, for example, you see we have 7 blocks here, and maybe we have allocated, I don't know, 100. So all this memory is allocated, but at the moment not used. If for some reason the code refines the grid, then of course more of these blocks are used, but we don't have the dynamic memory management in the strict sense. So even if you use only these 7 blocks, you have allocated the whole bunch of memory. And this is, say it again.
Sorry, and the maximum size of memory is given at the beginning.
Right.
Okay,
Precisely.
so the 2048, what you put at the beginning.
Exactly,
So
yes.
Okay.
Yes, and the code then computes, I will show it on the next slide how it does that. And the idea is simply, well, first, this on a supercomputer, you are usually alone. So just WABBIT is running, nothing else. So why would you keep other parts of the memory free? Because nobody will use it. On a desktop PC, this is different, but the code is not designed for desktop computing. It's for supercomputers, and you can use it locally. And in fact, modern compilers and operating systems, even if you allocate an array which is 200 GB large, and you use only 2 GB of it right now, then this will work on a small machine. So on my laptop, I can also tell it to allocate 64 GB, even though I have physically only 32, if I don't use all of that. But this is specific to the operating system. It is not something we do in WABBIT. So we tell the computer to allocate this bunch of memory, and that's it. That's what we do. So this allocation, again, so we pass this flag, in this case, let's say 360 GB. In the call, this is the total memory consumed on all CPUs. Well, it's simply a choice. And the code computes how many blocks we can allocate from that. So this is just from the log. This is what is put on the screen or in the log file when you run the code. So it says it allocates 360 GB, which per rank on this machine yields 4.5 GB. And then it computes, okay, I can allocate about 400 blocks on each of the CPUs for that. And now what we see, just a bunch of information, but what I want to point out is the grid is now allocating on one CPU, on the root, on rank 0, it is allocating now this heavy block array, which has a shape of 31, 31, 31. This 31 comes from the block size 23 plus the ghost nodes, as we have seen previously. It allocates 4 components, so UX, UI, UZ, and pressure, and about 400 blocks. And this is for one CPU. Every CPU allocates an array like that. And if you look here below in green, the LGT block array, every CPU allocates, of course, a much larger array. So not only the 400 blocks, but the total number of blocks. So this number times the 80 CPUs that are used in this example. So again, just to illustrate this concept of heavy versus light. So light means it's a small array and it's not very expensive, but it is for all CPUs allocate the entire array, while for the heavy one, all CPUs allocate a subset of the entire array. And you also note, just I point that out, we want to allocate 4.5 gigabyte here, but in fact, what the code reports, it's using only 3 gigabyte per CPU at this point, but it's put in green here. This is without the ghost node buffer arrays that I will come to a little bit later. So this is just to say, even if you have 4.5 gigabyte per core, you cannot use 4.5 gigabyte per core because you need some additional work arrays for MPI synchronization. Anyway, yes, and then a comment on efficient coding. So sometimes you will need work blocks. An example would be the task is you want to compute the maximum of the divergence of the velocity field. So what the tasks are is simple. You have to first take the velocity field, compute the divergence of it, and then take the maximum over all blocks, right? But for this task, you do not need to store the divergence everywhere. You can simply take one block, compute its divergence, take the maximum, store that somewhere, and then go to the next block, compute the divergence, compute the maximum, and then compare that to the previous maximum. If it's smaller, then you can discard it. So this is just an example, but it happens quite often that you need to do something and store it somewhere, but you don't need the whole array for it. And as you have seen previously, we allocate, let's say, between 100 and 500 blocks. They have roughly 20 components because not only the state vector comes into that, but also the right-hand side registers for the time stepper, the mask, the work arrays, and so on. So basically it is, let's say, around 20 or 30 components. So one more block or even 10 more blocks doesn't change anything regarding your memory consumption. So what you do in the code, please, is you use a snippet like that. They should be safe. So in Fortran nomenclature, this means persistent. They are not deallocated when the routine is over. And this is just the definition. So it's allocatable, and that's important. It's not on the stack, it's on the heap. It's safe and it's declared like that. And then you have these snippets just because it depends on the dimensionality, how large the blocks are. If not allocated, then allocate. And this code is then executed only once when the routine is called for the first time. This may seem, for those of you very familiar with high performance computing, something not so clever because we lose sort of track of how many of these blocks we actually use. But as their number is very small and they are negligible in front of the, let's say, if it's 100 blocks with 20 components, that's 2000 blocks per CPU. And we allocate, I don't know, 15 maybe additional blocks. So it doesn't change something in that regard. And they should be allocatable because, so this would be a definition which lies on the stack, where you just give it explicitly the dimensions already, and you do not have it allocatable. But then this may cause problems if the size of the block size is too large, then they don't fit on the stack and the code will crash unless you use this, in Linux, it's ulimit -s to increase the stack size, but please simply don't do it. It's not a good idea. Right, so that's about what I wanted to say on allocation and memory management. Now, I promised earlier the tree code. So we have a bunch of blocks and they are somehow distributed in space. And so how do you identify blocks and how do you know where they are in physical space? And we call this a tree code. It is either a quaternary or an octal number, so a number to the base is 4 or 8, based from some very old but extremely nice to read paper from the 80s by Irene Garantini. And she proposes a coordinate-based tree code, which is actually fairly simple. It's visualized in this diagram. So she just assigns numbers to directions. So 0, 1, 2, and 3, and this is a pity actually. Unfortunately, we implemented it also that way. So our tree codes are 0-based, but you will see later why this can be a bit annoying. So the leading 0 means you first go in the 0 quadrant. The second 0 means inside the 0 quadrant, you go in the 0 quadrant, so this one over here. And the 3 means you go in this 3 quadrant, right? So basically 0, then you divide it by 4, you go again in the 0, and then you go in the 3. So same here for all the other blocks. I think it's fairly simple. And this way, we identify each block. Now, this is a coordinate-based nomenclature. So why you call it a tree code is maybe not so obvious from this image, I don't know. But here it's actually a bit more obvious. So basically, each digit of this number means one branch in the tree. So you start from a root, then you have the first digit, which is 0, 1, 2, 3, and all of the other digits, and then level by level, you have the digits. And so this is why it's called a tree code. It's a hierarchical coordinate format. And what I want to point out is that in the past, or let's say I just go back one slide, what people used for these trees is pointers. Maybe I show it on the next slide. So basically you have a structure which is based on pointers. So each point has a parent node, a mother node, and so on, children, and the navigation in the trees is done by pointers. That, I believe, is not a very efficient way to do it. It has worked, of course, no question asked, but for what we do, this coordinate system is much better. It's working much better, and it is more reliable to do it. Yes, so if we now go back to our example grid, then now you understand why these numbers are here. These are the actual tree codes. So any of these tree codes uniquely identifies a block in space. You can compute its offset and its spacing just from these numbers. They are stored in this LGT block array. And again, keep in mind it's redundant. So all CPUs know everything. So if you say it's block number 15 or so, then the first entries of this until the params.max tree level are the tree code. Maybe we first look at it down here. So this is how the LGT block array looks like. Each line represents one block. And now if we look, so here's 0, 0, then -1, and so on. So this means this tree code has two entries, 0, 0, it is this block over here. And we store in this LGT block array a few things we really need very, very often, most prominently the level. So this number, this 2 over here means this is a block on level 2, right? You start from 0, it's just one block, then you go one level up, then you have 4 blocks, you go one level up, so 2, and you end up with this refinement twice. The 0 here is the refinement status. So we use that for flagging if the block is to be refined or not. And the last one, again, not understandable right now, is the tree ID if we have several trees in the same memory, but we come back to that later. And those constants, they are actually defined as a public parameter in globally in the code. So you have that everywhere available. Right. So, and well, one thing that I can actually say right now is that this is probably not the best way to do it. We started with that and we never had the time to change it, but this is actually an array. So it's a 2D array. whereas the original work by Gargantini actually uses just an integer for the first one. So the whole tree code in their nomenclature is one integer. For us, it's an array, but it's on the to-do list to change that someday. And what you also note is this array has a size. So we give it, of course, at the start of the simulation, you have to allocate it, so you have to give it a size. And this size here means, this is 3, 6, 9, 10 levels or so, we allow at most. So in the parameter file, this max tree level variable here is specified. So you tell the code a priori what the maximum level of refinement you allow. And this is done for several reasons. It's for memory, right? If you give it like infinite and you develop, let's say, a shock in compressible Navier-Stokes, then of course your resolution will just continue increasing and increasing and increasing until infinity. This is probably not what you want. So you say at some point, well, stop here. I at most refine 10 times or so. And the second, and maybe even more important remark is for error balancing. So depending on your parameters, a finite number of refinement levels is a good choice, but that again is on the physical and the mathematical side. We're not going to discuss this much more in the detail, just that you heard it once. So from these tree codes stored in LGT block, we can compute the spacing and origin. This is a general call to this routine. It takes the params, the ID of the block, the whole block array, and then it gives you back the x0 and the xy and dx. And this is in fact a wrapper for a routine which is in the tree lib, but I am maybe skipping a little bit on the details here. I just wanted to say one more thing. I will go back a few slides. I'm sorry for the confusion. What is nice about Gargantini's work is that she provides a way to compute the neighbor. So if you give it 0, 0, 3, 2, and you want the neighbor in the, say, eastern direction, then you have a way of computing from 0, 3, 2, 0, 3, 3, and so on, like this jump is also encoded. So that's the reason. From a tree code, you can compute the neighboring tree code, even if it's a complicated one like that, like 0, 3, 3, the neighbor to the right is 1, 2, 2. That's the reason why we want to have these tree codes, because that's obviously used for MPI parallelism. Good, I go back to the slide where I was. Now, okay, so this is also something that you need to understand if you want to do anything with that code, and it's really a central concept. You have seen the grid changes over time. So of course, the number of blocks that is currently used is not fixed, right? In the 3 vortices case, you start with 7, you end up with 400. Okay, so obviously it's not fixed. Now, this is how this looks like in memory. So you have the heavy block arrays, and I just plotted here 3 CPUs just to make it visible. So each of the CPUs allocates its own heavy block array, and each of the CPUs allocates the whole LGT block array. So this means this little chunk of heavy data actually goes here, and the blue one over here, and so on. So here, you just to illustrate it a bit visually, how this chunking is performed. And so we can assign each block a heavy ID, so the index in that array on the CPU. They always go from 0 to n, where n is the maximum number of, no, from 1 to n, I'm very sorry for this typo, from 1 to n minus 1, where n is the number of blocks that we allocate per CPU, so the number that we have seen in the log file previously, let's say 400. And this is called the heavy ID, so it's simply the ID here. And each block also has a position in the LGT block array, which is unique. So here, all CPUs have a block with the heavy ID 0, right? But they are corresponding to different light IDs. So this one here would be heavy ID 0 on the blue one, but its light ID is, I don't know, 8 or 9 or what, how many squares I have plotted here. So there is subroutines that you need to know that, to convert. So convert a heavy ID to a light ID, convert a light ID to a heavy ID. It's essentially a one-line formula, but we just encapsulated it in these functions so that we can change the way this is done in the future much more easily. Right, so this is number of blocks, so this is computed from the -- memory that you use. And well, you see, well, Julius, you always call it a telephone book. So basically what we know is the LGT, this chunk of LGT blocks corresponds to the second CPU. So it has an offset telephone, like a pre-dial, Vorwahl of Deutsch, and then it has a number. So this is called the telephone approach. Now this still doesn't tell you what we do if the number of blocks changes. And this is called the active lists as promised. So this is the situation maybe on the CPUs. So CPU 1 uses this block, this is unused, these two are used and the other ones are unused. CPU 3 uses these 3 blocks currently, and CPU 3 uses just 2 blocks. Right? It is possible that this layout contains holes. It's very simple to understand. If you merge 4 blocks into 1 block, or in 3D you merge 8 blocks into 1 block, then this leaves 7 blocks empty. So even if they are neighboring in this array in the beginning, after merging it leaves a hole of 7 blocks, which the code will subsequently fill when new blocks are generated. They will be put in these holes first, and then at the end appended if necessary. But it is not guaranteed that this array is always continuously filled. So what we could do, but what is stupid, which is why I put it here, we could always loop over all our blocks, yeah, right, from 1 to params number of blocks to 400 blocks, and then we could check for each of the blocks if it is active or not, and then do some stuff with it. But that's stupid because it is an n-square loop, and most of the blocks are probably not active, and you do that every time, so you have a huge overhead from that. And the solution to this overhead is the active list. So basically, you realize on CPU 1, only the blocks 1, 3, and 4 are active. So you would like to have this list 1, 3, and 4. And you get it. You get heavy N. So the number of active blocks right now is 3. This array, heavy active, is also fixed in size, as all the other arrays are. So this is an array which has n entries, and only the first 3 are used. So we will see in just on the next slide how a typical loop looks like. On CPU 3, it's the same. So blocks 3, 5, and 8 are used, and on CPU, I'm sorry, this was CPU 2, and on CPU 3, only 2 blocks are used. And this is well possible. It is not guaranteed that this number is always strictly identical on all CPUs, because sometimes the number of blocks is not divisible by the number of CPUs. So then this number may differ slightly or even drastically in the initial condition. Now, for the heavy active list, this is for each block, for each CPU, which blocks are active, and the light active list is globally which blocks are active, right? So this has a total of 8 active blocks, and it's just a union of all these entries, but of course converted to a heavy ID, right? So for the 0 CPU, this is just 1, 3, 4. And for the second CPU, so these indices over here, they correspond to 11, 13, and 16. And these 2 orange ones over here, 6 and 7 in heavy, but 23, 22, and 23 in light. So this is the active list. And they are computed in this function that I'm not going to go into detail. So typical task in WABBIT would be, just to have an example, to make it a bit more practical, please set the function f, which is x plus y plus z, everywhere in the code, on the grid. So this is a heavy operation. It does something on the blocks, and it's parallelized, right? Each CPU executes the same code on its local blocks. And this code looks like that. Please ignore this, this tree ID flow. Just for now, we will talk about it a little bit later. So the first is it loops over the heavy blocks, heavy N, okay, 1 to heavy N. This means all CPUs just work on their blocks and on their active blocks. Then it extracts the currently active block from this heavy active list. So it knows now where to store the result, right? This is the heavy ID over here. It converts heavy ID to light ID. So it computes this LGT ID in the global array. It will need that. Then from that, it computes the block spacing and origin from the light ID. And now we can do something on the block. So this is really typical loop that you see almost everywhere in the code. Looks like that. It has these 3 calls before doing something, and then it goes in the block and it loops over the Z, Y, and X direction, just as we have shown previously. And this line over here computes the coordinates. Now, unfortunately, I forgot to put a figure here, but you remember that the origin of the block is the first interior node, not the first ghost node. So you remember you have an interior of the block, and around it, you have the ghost nodes. So you will have to use this offset times the spacing plus the offset to get the actual coordinate. And you do that for Y and X the same. And then you can store at the position X, Y, Z, first component. And in the heavy ID, you store the result of this operation. Okay, this is how a loop looks like in WABBIT. Right, so this actually explains the data structure, how it's allocated, how it's used, the active lists, heavy versus light. So this is what we need to know if we deal with the code. The next thing, so from now on, it is going to be more brief. Conceptually, I'm just going to introduce the concepts rather than going in the very much into detail. What we need to know is the neighbor relations. That's particularly well, it's imperative for MPI parallelism. So the way we do that is this heavy neighbor array. So for each block, which has of course a heavy ID, we store the light ID of the neighbor in a specific direction. So in 2D, we have a total of 16 different directions, which is because they are all unique. Here's an example for this block, this cursor block, and this is why it's not a small number, but it's a fairly large number, is its neighbor, and this neighboring relation is called 14. So there's a table for that and with a lot of figures. But this is the relation. So this would mean for this block in the array entry number 14, the light ID points to this red block. If it lives on the same processor or not, it's just a light ID, so you can compute the processor ID from the light ID. Right. So, and if this code is -1, then it simply means there is no neighbor in that direction, which is well possible because if you imagine, like say, this gray block has a neighbor on the same level, a red block, which I think is neighbor code 2 or so. But if it already has a neighbor 14 in that direction, it cannot have neighbor 2 in that direction. So that's simply this -1. And in 3D, because it's, well, there's a lot of cases, there's a total of 74 possibilities. And this is only for graded grids, so a jump of 2 in resolution. I don't know how large this number is if you allow changes of resolution by a factor of 4 as well, but it's going to be fairly large. And for each of the 74 cases, we have to program, well, we have to program each of these cases. So that's one reason why we use graded grids. How are these neighbors found? The routine is called update neighbors. So it actually just fills this neighbor array. It is parallelized, as the index heavy suggests. So each CPU works only on a chunk of the data. it computes the neighbor code as we discussed by Gargantini's work, first on the same level, then one level up, so the neighbor may be coarser or the neighbor may be finer, and then it checks if it finds that block in the light ID list, and if so, it stores its light ID, otherwise it stores -1. Right, and this check if that block exists, this just what I say sort of naively is of course not so easy, because what you would have to do is you would scroll the whole LGT block array and see if you find that block. This is an n-squared operation. So basically for all blocks, you need to check all the blocks, so giving you n square. And it's incredibly slow, even though our light data is not very large. So we did that mistake in the very beginning of the code 4 years ago. We just said, well, it's light data, it is cheap, so we can do even stupid stuff, but it turns out we cannot. So this routine is called does the block exist? You give it a tree code and it tells you if it finds the block. And this uses this sorted numerical list. And this list is actually more in the spirit of what Gargantini wanted to do. So if we have a numerical, if we have a tree code like that, 0, 1, 2, 0, 1, it will convert it into a 1-based tree code integer. So all of these digits are just at 1, and it's of type t size. It's a large integer. And this actually limits the number of refinements that we can make in the code currently to 18. So 18, this is the maximum number of refinements we can handle, because otherwise it blows up this integer precision. And this list is sorted by tree codes. So it's yet another list, and it just contains these numerical tree codes and their light IDs. So if you find one, if you're looking for a specific block, this is the way to go. And this is very fast actually. And in the future work, we should actually get rid of the array structure, so of this list here, and use only numerical tree codes. But as I said, this is, well, if ever we have time. Right, so if you have more than one tree, you have what's called a forest. And this may be not incredibly useful for you right away, because it's mainly for Philip's work for post-processing in the model order reduction, where you actually have a collection of snapshots and they all have a different grid, a different tree. So in the code, grid and tree is the same. It's just synonyms. And now you could have, again, stupid ideas, and you could say, well, for each of the trees, I allocate one heavy block array, very large, and then I work with that. You shouldn't, because it's very inefficient memory-wise. So even if we have several grids, we still have only one heavy block, one LGT block array. And it's just an additional parameter which tells to which tree belongs a certain block. Now, if we have a tree, and this is why I'm telling you that only because it's confusing in the code right now. The history is that we started with a single tree, used that for a couple of years. Then Philip did his beautiful work on the multi-resolution, where he needed a forest. And he did a very good job in the beginning, separating his post-processing from the actual simulation. So this is actually beautiful work. So keep the rest of the code completely unchanged and simply add a layer of forest, which is only used in post-processing. Perfect. But later it turned out that I wanted to use the forest also in the simulation parts because of the mask function. So the time-independent part of the mask function is on one different grid than the flow. And this means if you have routines that deal with a single tree, this is how the arrays look like. This is just an integer. It is not an allocatable. A 1D list, and a 2D list. And if you have a forest, then you have one of these active lists per forest, per tree, I'm sorry. So maybe tree 1 has only one block, then it's heavy N is 1, tree 2 has more blocks, and so on. And you have an active list for each of the trees. And at the end, the very last entry in these active lists of both heavy and light is the union of all the trees. If you want to do something which affects all the trees, for example, deleting them. And while this is a figure I took from Philip's work, because it is very nicely illustrating. So we have grid omega 1, one tree, grid omega 2, which is different. And this is how it looks like in terms of the tree code, right? The colors really correspond to different, to the blocks. And we have, well, you see that here it's separated. So this is tree number 1, and this is tree number 2. And in future work, I would really like, if I have time, to remove the trees. So simply have all routines called forests, because it's getting quite messy at the moment. If you have a forest or a tree routine, you have to pass a different subset of these arrays, right? It's a bit annoying, but it's not a big deal neither. And in the simulation part of the code, we use 3 trees, which is tree ID flow. So this is the most important tree. This is where we compute the state vector. And we have a tree ID for the mask and the mask cursor, but I'm not going into detail about that. But what you see is Philip drew this beautiful dashed line over here. And this is a space filling curve. And it's important for the next part of our presentation. So it simply lines up, it visits all blocks in a certain way. It's called the Hilbert curve. And this is used for load balancing. So basically on the right, you have a 2D grid. On the left, you have a 3D grid, and how it is distributed among processors. So each color is one processor. And you see this green one over here, for example, it holds a bunch of blocks, white. So the code is tuned that all CPUs hold approximately the same number of blocks, plus or minus 1, 4, or 8 blocks if it's after refinement. And you see that these space filling curves have the nice property of preserving some of the localities. So in other words, these blocks here are on the same CPU. They do not need MPI communication, whereas these blocks here are not on the same CPU. So to synchronize their ghost nodes, we have to use MPI communication. But some locality is preserved. The subroutine is called balance the load. It first decides how many blocks each CPU should hold, then computes the space filling index, as we have seen on the previous slides, and then distributes contiguous chunks of the space filling index to CPUs. And you can see in 3D it's the same. It's just a bit more difficult to visualize because, of course, it's a volume now and not an area which is held by each CPU. So this is one part of MPI parallelism, 1 out of 2 only, actually. So in many, many parts of the code, you actually don't see any of the MPI stuff. It's just balance load, which is probably not the most important. And the next one is the synchronization. And this is actually really the very heart of the code. It is super complicated, but it is extremely important for performance, because this is where it is decided if we have a useful code or not. This whole business, active lists, block data layout, and so on is all very, very simple and not complicated at all. It works like a charm. It is perfectly parallel, so it scales 1. There's no loss in any parallelism, but the synchronization of these ghost nodes, this is where it gets really messy and complicated. So the basic idea is just visualized here. I have a sender block, and I have marked each of its point by this little S's. The yellow ones are the interior nodes. I have the receiver block. The pink ones are the interior nodes. And now my task is, for example, I want to synchronize this layer of, this layer of points on the receiver, so the corner neighbors on the receiver, with data from the sender. So this is just a visualization. We're talking about these little squares here. The green square is the receiver square, and the red square is the same, but on the sender. And you can already see with the overlapping R's, maybe it's not super visible with the colors, I'm sorry. So some of the R's correspond to S's, and those are copied, right? So the operation looks simple. It's not super complicated neither. You just need to figure out what is this index, compute which blocks on the sender correspond to that, and then extract those and send them via MPI. doesn't sound so complicated, but it is complicated. And oh yeah, and I actually forgot to mention that earlier. I am very sorry, I should have said it right at the beginning. Our blocks have redundant nodes. I don't know if I go back to the maybe I go back to the beginning of the presentation. I am sorry for that, but it's actually so important that I want to show it to you. So this is our grid definition that we've seen in the very beginning, and these lines here where the blocks actually touch, those points are redundant. I have actually put it here, but I forgot to talk about it. So these points are actually held several times in memory. They are part of both blocks which touch, or in the case of this corner neighbor, of 4 blocks, and in the case of 3D, it may be even 8 blocks. Okay, we have them redundant in memory, and that's just, we need to know that. There's good reasons to do that. It is still like the lesser of many evils, let's say, right? It's a bad idea to have stuff several times in memory, that's for sure. But among the available options that we have, this is still the best that we can do. So for technical reasons, not mathematical, and currently I don't see a way around it, but just keep it in mind, those are redundant in memory. And what does that mean? That sounds super simple. You just hold the same value twice, but it's actually not at all simple, because if you look at this line over here, they are redundant, but they are on different levels. So on the fine block, there's more points than you have on the coarse block, which means these values over here, this little guy is interpolated on the finer block, on the coarser block. So by definition, the values are not identical, right? Because one doesn't even exist on the coarser block. So of course, the value is different from the finer block. And this sort of subtlety creates the trouble in ghost node synchronization, because you must be very careful what you do, in which order, and so on. But again, I spare you the details. I was just hoping that someday somebody would come up with a better solution, just to motivate you. This is one of the big issues that we have with the code. It's about 40% of our CPU time are spent on this synchronization. And this is the reason why we do not get perfect scaling. I'm taking a lot of time. I am sorry, it takes much more time than I anticipated. If you have to leave, please leave, right? I'm sorry, I didn't practice before. One more thing that you need to know when dealing with the code is unit tests. We call it unit tests, but they are not unit tests, but rather they are very small simulations that are run in a scripted fashion. A unit test is ideally something that checks individual routines of the code and sees if you did something stupid. But at the moment, we don't have the capacity to do it. And the unit tests that we have are really a lot better than nothing, because many research codes do not have any of these tests. So I'm actually not, well, I'm at the same time embarrassed and proud that we have it. They are usually called with the make test command, and it runs just a predefined simulation where I've stored the parameter file somewhere in the repository. It runs it, takes the HDF5 output, computes what we call key values from it, so the minimum, the maximum, the mean, the sum of the squares, and so on, and compares it to results that we have obtained earlier. And if it's the same result, well, that's nice. So we have code still produces the same result as before. That's the meaning of the unit test. It doesn't necessarily mean that it's correct, right? It could have produced garbage before and it produces the same garbage now, but at least you didn't screw up with respect to previous code versions. And what the drawback is and why I'm embarrassed of this stuff is the interpretation of the results requires experience. So if some of these tests fail, then you don't get a pointer what went wrong. You just know something went wrong, and it's of course related to what you did with the code. So that's for sure. So you will have to think what you have done and how could it interfere with these tests. And this is unfortunately some some work, which is why I recommend to run these tests as often as possible while changing stuff in the code. If you break something by accident, there is at least a chance that one of the, I think it's 20 unit tests right now, could catch this mistake. But again, if all the tests are successful, it does not necessarily mean that everything is correct, because we would need thousands of unit tests to really check every setting in the parameter file. Well, this is how this looks like on the screen. If you hit make tests, it just runs these unit tests and then says pass, 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 and sometimes it says fail, and then you will have to look for your error. And in future work, if somebody has the time, it would be much nicer to rewrite this whole script in Python, because the bash script is really messy, and it would also be good to store the HDF5 files somewhere. The reason why we don't do it right now is Git. So Git is a repository management system that stores all previous versions. So you can go in the Git repository back to day one in 2015, where we started this work, and all the previous versions are stored. It's done incrementally, but for binary files such as HDF, it cannot work this way. So actually, if you change the code, if you change the H5 files, it means it will create a new HDF5 file, and so on. So doubling the memory effort every time you change something in the unit tests. And to avoid the huge, that you have to download a 2 GB repository when starting, we did not include it. But it is probably better because it's easier to see what went wrong with the code. Well, that's for future work. So we are nearing the end. Good news. As I said, WABBIT is separated in WABBIT itself and the physics modules. That's how it's called in the code. The idea is WABBIT handles the grid, the topology, and so on, MPI, and the physics module decide what happens on the blocks. So this means, by definition, the physics modules cannot see, in some sense, the entire grid. Why we did it is, the idea is that you can take existing codes that you have developed someone in the past on monoblocks and simply add them to the code. Currently, we have 3 of them. The artificial compressibility module, this is what I do for insects in the videos at the very, very beginning. We have the Navier-Stokes, which is actually also the compressible Navier-Stokes, so really with shocks and everything in skew symmetry. And the convection diffusion module, I think it's also mainly my work, is mostly used for testing. So transport equation and diffusion problems, very good, because very, very fast for testing. You notice the nomenclature is a bit noisy with all the new, but well, what can you do? And instead of using all the 3 of these codes, using in terms of Fortran use statements, we use a meta module. So this is the meta module. It's simply called also this way, physics meta module. And here it's just included the different physics modules, so that in the WABBIT code, we always just use this meta module, and it itself encapsulates all the other physics modules if in the future we want to add something new. And of course, well, this is also a very essential thing to know about Fortran. Just specifying private without anything means that everything in this module is private. It cannot be accessed from outside, except for those marked public explicitly. And you see that each of the physics modules will have to provide a routine for all of these tasks for reading its parameters, so that WABBIT can tell the physics module, now it's time to read your parameters, to save the HDF5 output, to call the RHS routine, so the actual equation that we're solving, to compute a time step that also depends on the physics module. WABBIT cannot do it without knowing what actual equation is solved. For the initial condition, how the output is named. This is used in wavelet thresholding. Maybe we don't go into detail. For statistics, if you want to do, I don't know, compute the sum of the mask function, for example, or the forces, this is done in this routine. We have filter, which is, I will come back to that later. Filter and adaptivity is similar, but yet we have distinct distinct functions for that. Creating the mask function in the penalized case, and initialize the log files. Right, and just an example. So as the physics modules can never see the full grids, it's always WABBIT's task to make the grid transparent in this way. Sometimes the physics modules will have to do something which acts on the whole grid. For example, forces. The force is a sum of, let's say, the velocity over all blocks, simplified. But as the physics modules cannot access the blocks, it means, well, it's impossible. And to make it possible, WABBIT has these wrappers. They are always called _wrapper, and they call different stages of the same routines. So in the initial stage, for example, is called only once and not for all the blocks, performs the initializations of the modules, such as resetting the integrals, right? Sets force to 0, for example. If we keep it for the force, then it has the integral stage. This is actually called for all the blocks, and it does call the RHS with integral stage. So in this case, summing up the force locally on each CPU. In the third stage, the post-processing stage, the MPI or radius is performed. So now all CPUs gather their result, sum it up, and give the total force over all CPU. And then we compute the local stage. This is the actual derivatives. And this staging concept is done in many more places, okay? Because, but this is how it's done in the code, because at many places you need to initialize, then do something, and then have some post-processing for that. The MPI already uses the typical example. And also, so this kind of comment in the code, I would encourage you to do that. As you can see, it's not well, it's text. You should actually write some text. And this text should actually contain information you cannot see from the code that you type. So, or not trivially see. So, because at many places you will see past students have taking joy of writing just call RHS meta within its stage, and then they have a comment before that it says call RHS meta within its stage. But that I can see from that code. The question is, why do I do that? How? And so on. These are the questions you have when you look in the code. Well, almost done. Second to last slide is the grid prediction and time stepping algorithm. This is the only mathematical part that we have inside it. I'm not going in the details again, but it's called refine, evolve, coarsening. It means we start with a grid, which contains our solution at the time level t. Then we refine the entire grid once. There's reasons to do it. It's to resolve nonlinearities, because we cannot be sure that the grid that we start with, well, we can be sure that the grid that we start with is appropriate for the solution. That's what the algorithm does. But we cannot think that it's also enough for the whole time step, because during the time step, new small features may emerge, and they are not resolved on that grid. And to be sure that we catch them, we first refine the entire grid, then apply the evolution. So this is the actual time stepping. And then we remove blocks which are not used. This is the algorithm. And then in the last step, we have the load balancing. So this is what we would tell people on conferences. And this is how it looks like in the code. I have just deleted many, many lines, as you can see by these dots here. This is the main time stepper loop, do while the time is not reaching time max and the iteration number is small, and we keep running. Keep running is for error catching. You can use the code without adaptation, of course. You can use it on a fixed grid, then you just turn this adapt mesh to false. But if it's not, then it first synchronizes the ghosts, refines the mesh, so that's the first stage over here. Then it calls the time stepper. And this little internal loop here is used for very special circumstances when we want to do more than one time step before evolving the grid again. This is typically what we do in bristled wings, because if it's very, very viscous, then it may be good to perform more time steps on the same grid. This reduces the overhead of adaptivity. Then if it's not no filter, we apply a filter to the blocks. Of course, we have to synchronize the ghost before that. Then we do the statistics. There's a bunch of conditions for that, specified in the parameters file. And after the loop, we adapt the mesh. And then we go to the next time step. Right. I have on the very last slide just the governing equations for the artificial compressibility method, but I don't think we're going to discuss it now. Okay, well, thank you so much for listening. This was, well, let's say, introducing some key aspects of this adaptive code. And well, if you have questions, now would be the time.
Thank you very much, Thomas.
Thank you for listening. So are there questions?
Shall we raise hands or?
I don't know, you just speak.
Yeah, well, maybe I ask the first question then. Is there a way to check how much memory you need for a computation, at least to start the computation before actually starting? So, like, for example, on a uniform grid, it's kind of easy to know this. And for the adaptive code, it's sort of doable, I guess, because, well, you have a rule where you originally refine, right? So, or that's not possible at all. Like, I don't have a machine with full memory of the supercomputer. I run the computation with a, I don't know, some parameters, or not really run, but kind of pre-run.
Well,
and yeah.
Well, it depends. So it's always the answer. It depends.
Okay.
So if penalization is used, then you should usually tell the code to refine on the mask function as well. This keeps the fluid-solid interface always on the finest level.
Yeah.
And in those cases, after the initial condition, the grid is often close to what is used during the simulation. So then you know right after the initial condition if you have enough memory or not. And you can compare how much the code allocates and how much it actually uses. But knowing a priori how the memory will behave is unfortunately not possible. But you can.
No, it's not how it will behave. It's just that well, actually my question is very practical. So for me, waiting time from submitting a job to actually having this job started is like 3 days, for example.
Oh.
Right? And I always have to use trial and error to find out how much how many nodes, how large L max I need to set finally. Let's say I can have 50.
So how much
50,
you allocate?
50 nodes max. So I know how much memory I have. I cannot have more, but okay, can I afford this computation or not? And I really need to submit. Well, I don't know how many jobs to. It amounts to a month.
So let's say for parametric studies, you often have a very good sense of how much memory will be consumed. Like if you, for example, just vary the kinematics of a beating wing, then it will be kind of similar, and you can just add 50%. Now, if you start something completely new, then you have no choice than to start from a relatively coarse resolution, uncheck how much memory you need.
Okay.
And then you can say, well, a rule of thumb is if you increase the maximum refinement by 1, the memory increases by about a factor of 4 to 6. That's okay, what I observe typically, but of course it depends, right? If you're very far away from the asymptotic, so super coarse resolution, it may change even more, but 4 to 6 is a rule of thumb.
Okay, I see. Thank you. Okay.
I have a related question. And when you find out that you're running out of memory, can you restart your code or?
Yes. So the code does check if the refinement stage will result in out of memory. If it does so, then it will dump a backup to hard disk and then fail. But unfortunately, that is in about 90% of the cases, it will work. But sometimes we have, well, most of the time it will work, but sometimes this occurs during MPI load balancing problems. So if we distribute the load and the load is very much imbalanced at the start, then it may happen that the transfer does not succeed. And in this case, no backup will be dumped and the code just fails. But most of the time you can resume it right away. And at this point, you would also then, ideally, you script all that. This is in my case on the supercomputers, I do it like that. I have a job file which is self-resubmitting, so it actually submits after the run again. If the maximum time is not reached, it checks if the backup is complete and so on, resumes the backup, and then restarts the code. And at this point, we could also decide if we need to increase the number of nodes, but that I didn't currently implement. Because in the end, well, let's say in most simulations, the number of blocks that we have goes up at the beginning and then sort of saturates. This is what most of the time we have. Or it decays, like in the 3 vortices, start with something fine and then end with something very coarse, then of course it's easy. Yeah.
And you mentioned that some memory is allocated for light blocks. I didn't really understand the point of so the parameter passed when you start MPI run is the amount of memory including the light blocks.
Yes. Yeah. The code computes from even including the ghost nodes, because they also need special buffers for that. Including the ghost nodes, the code estimates how much memory it needs, and it's kind of precise. So it's the maximum amount of blocks you can allocate for the memory, including light and buffers and all the lists.
Okay. And do you have an idea how much memory is allocated outside from this amount which is stated in the MPI run statement? Do you use some memory?
No. So the amount of memory outside, there's none. So you tell it to allocate 2 terabyte and it will actually allocate at most 2 terabytes.
So it will not use any.
Very little, if any. And probably less than you tell it to, slightly less.
You checked that?
Yeah, I checked that. Because the ghost nodes is a one-dimensional buffer. And so theoretically, the worst case, if a CPU holds, let's say, n blocks, and they all have all their neighbors on different CPUs. And so we allocate enough memory to store all the ghost nodes layer in this buffer. But this is a very unrealistic case because many neighbors are actually local and they are not stored in this buffer. So this is why we actually allocate too much memory, slightly.
But
the very tiny work arrays, they don't contribute to memory consumption. So I checked it on our machines. We really are bound by this 2 terabyte that we set. So, or whichever memory you say, it should be this number.
Okay.
If everything works well with the compiler, and that may be the case in your case. I don't know if some type definitions, the integer precision or real precision is not the same as, well, that it's designed for, I think, 8-byte integer and double precision. So if the code runs on single precision instead, then you allocate way less memory than you tell it to.
No.
But if it runs on quadruple precision, then, well, but these are things that may be different, yeah.
Okay.
I have a quick naive question about the corners and the redundant points. I'm just wondering Well, we know fine winds for the interfaces.
Yeah.
But it happens at the corners.
Same, fine winds. There's two, well, I'm sorry, but just the ghost nodes is another 1 hour talk. So at the corners, it's the same. If the neighbors are finer, then the finer blocks override the coarser blocks.
But it's not unique, not necessarily
No, it's
unique.
not unique. And the secondary rule is the block with the higher light ID wins. Because the on the same level, the nodes should be identical, and they are not. They're identical to machine precision. And in the past, we thought that this creates errors, so that this difference can grow. Today, I am not so sure if that was a correct conclusion that we have reached, but in any case, we do have rules that make the grid unique, in the sense that every point is synchronized from exactly one block and not several blocks. I'm not so sure if that's still necessary or not, and it may have been a different story, but
No, better have this, because otherwise, yeah, maybe it's not necessary, but then for some reason it becomes necessary.
well, this rules make, of course, the ghost node synchronization extremely complicated. This is what makes it complicated. Because I don't know if you remember, but at some point we changed the grid so that it is actually unique. We got rid of the redundant points, but this creates other problems. It's unstable.
Yeah, I remember. That's a point where I started doubting about memory management in the code, questioning this.
Yeah, exactly.
Okay. Yeah, another question unrelated. Well, maybe Philip can answer that one. Is the compressible Navier-Stokes there? How functional is that one?
Actually, it's if all the unit tests work on your machine, then it should be working. There is also, if you go to the Doxygen file, so we have some kind of online documentary. There's some kind of overview of the modules, how they are structured.
Oh, I see.
So you see how everything is connected to all the other modules and what kind of functions are already there. If you want, I can provide you with this. I have a nice PDF which shows all the unit tests done in this compressible Navier-Stokes file and how everything is set up. I can just send it to you if you want that.
Oh, thank you.
Yeah,
I forgot to mention that. Yeah,
that would be interesting to have a look.
Well, but
I wasn't.
For the compressible Navier-Stokes, Philip, so this uses filters, shock filters, and we don't actually know the interaction with the adaptivity right now. So as we had some problems with the grid jumps in the ACM module and the compressible Navier-Stokes, but we didn't go to the lifted wavelets.
I mean, what I know from my experience with this compressible Navier-Stokes is that if you use explicit filters, it doesn't very well work. But if you use like some kind of adaptive filters, like this bougie shock filter, then it works. At least I was running this SOT shock tube, and it perfectly worked also with adaptation. So from there, I thought everything should be.
Yeah, but
okay.
Only with the CDF40 wavelet. I don't think it has been tested
course.
with the lifted wavelets.
That's true. Should be it.
No, but yeah, if you have shocks, you know, claiming fourth order is well.
Well, but just those that can be a problem for acoustic waves, for example.
Sure,
because they channel
yeah.
the grid interfaces. But
no, I'm more just basically the compressible Navier-Stokes even without shocks. I was curious if it gives reasonable results.
Yeah, it gives very nice results. Actually, we published papers with this already on the. We even have a rotational symmetric right-hand side there with symmetric boundary conditions on the rotational axis, and we actually calculate this ion funnel with this, and we about to publish a paper on this already.
Oh, I see. That's interesting.
Oh, but so Philip, maybe you can give a talk on that.
Yeah, that would be
Just.
So
I mean, it's not really my research topic. So maybe you should go to the talk of Laurent. He's defending his thesis in, I think, 1 or 2 months, and then he will speak about it. If you're interested.
Well, the idea would be to create from this presentation sort of, I mean, it's not exhaustive, so we should actually give a series of lectures and put them on YouTube so that people can understand. And this may be the easiest way to document the code.
I think it's also very nice because now I'm really aware again of how nice this code already is and what we have accomplished so far. I mean, really.
It has been a long road, yeah.
It's really amazing. It's like that, yeah.
I have 2 questions about the compressible Navier-Stokes solver. Can you go to the limit of very low Mach numbers? And
Yes.
does it behave similarly to the artificial compressibility? And the related question is, what are the boundary conditions you have in, or which options do you have for boundary conditions for the different quantities?
So the Mach number, I have checked this in my master thesis. I can send it to you. I mean, what I've basically done there is I've looked at the vortex shedding behind the cylinder, and I've compared it to literature results, and it fits to the literature results. So I think this is doable, or it's fine. And I mean, from boundary conditions, what we normally implement is volume penalization. And now Julius has this special penalization method where we can do slip and non-slip boundary conditions. And but we can also do, like on the domain boundaries, we can do symmetry boundary conditions, or even in and outflow. This is also already implemented in the advection diffusion system. I have implemented some basic checks there for in and outflow boundary conditions.
I'm sorry, I removed those when adding the symmetry boundary condition.
Okay, good. So
in the convection module.
If so, well, non-reflecting boundary conditions would be something good to have in this code, I would guess.
It can be done, yes.
Well, like
and there are some features inside already which can be used.
So for the non-reflecting boundary conditions, well, I sort of gave up on that when I realized that people also use sponges in addition to non-reflecting boundary conditions.
Oh, right.
So
yeah, I remember.
But, well, then seemed to be intuitive to just use sponges.
Okay.
Because I derived the boundary conditions at some point, the non-reflecting ones, but well, if a vortex pair leaves the domain, then this almost inevitably create noise. That's you need a sponge.
And for compressible Navier-Stokes, you would guess it would be the same situation where you need sponges.
Yes.
Okay.
According to Matthias, you need sponges, yeah.
Okay.
It's been used for aeroacoustics already?
No.
But it's, I mean, now they are thinking about doing this because of the new volume penalization and because they are thinking about really complicated boundary structures, and then they want to go to adaptive code again.
Oh, really? Okay, that's planned.
And I have actually shared this file with the Navier-Stokes inside the chat if you want to see that.
Yeah, I received. Thank you. So you say you have circular. You can have circular jet, or what is it called, round jet?
Yes.
So,
can do that. And this is already, and this was also benchmarked, but it's not in this PDF here. I benchmarked this with a bachelor student once, I think.
Oh, I see.
Again, thinking loudly, can we run the insect simulations with a fully compressible Navier-Stokes?
I mean, the mask function is pretty much the same. It could be done, yeah.
Yeah, with minor modifications, it can be done, yeah. Not out of the box, but it can be used.
Very small time steps, then that will be much smaller than with the artificial compressibility. Or what would be the drawbacks using the fully compressible Navier-Stokes?
I would say the right-hand side is not that much optimized than it is in the ACM module. Other than this,
that could be an advantage because you are saying it is Q-symmetric, so it would be conservative then.
Well, but Kai, it is conservative in terms of the discretization, but of course the code is not conservative.
Yeah, this is
wavelet part is not conservative.
And I have to say, I've never looked at this energy conservation with the skew-symmetric equations which we use, because I mean, also in Julius' paper, he didn't give a real proof. I mean, he gave a numerical study about this. And yeah, I have never checked it myself so far, so I can't comment on that.
My question is it a major difference between fully compressible Navier-Stokes and the artificial compressibility? Could it be an advantage for us moving to the fully compressible Navier-Stokes?
Well, so the computational cost is much higher. You need much more derivatives to compute the state vector. I'm not sure in the small Mach number limit, the time step restriction may actually be even worse because you have the physical speed of sound, which may be even larger.
Yeah.
And you will have to implement the boundary conditions. So the insect module can compute no slip for the velocity, but I'm not so sure what needs to be done. Well, maybe pressure is fine, maybe not, I don't know.
Temperature, what is in the state vector? Temperature, entropy, what is used?
No, pressure.
Yeah, but even not pressure, like
Formulated
skew-symmetric pressure, like some transform, which is also why this Navier-Stokes module is, well, let's say it's even more difficult to use than the other one because it has some state vector conversions. It uses non-primitive variables, let's say.
I mean,
yeah, sure.
Before you can really use the bumblebee at this level as we use it in the ACM, many checks have to be done. First of all, you have to check all the properties of for simple test cases, which hasn't been done in this code. I mean, you have to validate basically very many things before you really can do rigorous calculations as Tommy is doing this with RCM. And it would be at least a master thesis, if not more than this.
Okay,
so,
sure. And a last question to this compressible business. When you're using CDF44, do you have the same problems as with the ACM?
I have never run CDF44 in the compressible Navier-Stokes yet.
It's not been tested.
I'm not using it anymore so much because mainly I use ACM now for my model order reduction things, and yeah.
So we don't know, in fact.
We don't know it. Yeah.
But Kai, why are you asking? Is it because you want to have acoustics for flapping wings, or?
Yes, this is it.
Well, Kai, maybe this summer. But maybe this compressible business is maybe not good for you.
No,
actually it needs to be edited later. So maybe.
No, I'm actually started asking because I'm thinking about, well, you know, my new job is more about industrial kind of flows. So they need jets and maybe plasma, well, as plasma arc inside a jet.
Okay, but on with jets, we have quite much experience with this code.
Awesome,
we have at least 2 master theses on jets with this compressible Navier-Stokes right-hand side and with this and with the WABBIT code. So
we should really put them because I didn't know those. We should really put them on the website.
I mean, first of all, my master thesis was the ion funnel, which is basically a under-expanded jet. Then there was this plenum, which is basically over-expanded jets. Then we have various kind of jets in this thing.
Oh, that's really great to know that.
Therefore, I would also suggest to speak to Julius because he is much more aware of all the things we did so far with this.
Yes, thank you. Sounds cool.
Okay, good. But I mean, essentially, this talk was for Hang. So I hope you have a better feeling of how this works and what you would need to do with your mask function and the pressure interpolation. Because those are the things that are on your list. I think this was the motivation for this presentation.
Yeah.
Good. Well, I will maybe stop the recording at this point.
Maybe let's make a break now. I don't